One.
Good afternoon everyone, my name is Terry Ben. So today my team and I will be presenting our project on the topic of round robin scheduling, one of the most widely used CPU scheduling algorithm in operating system. I will begin by giving a brief overview of what a round robin is and why it's important. In essence, round robin is ensure that every process gets an equal share of the CPU's time, making it fair and efficient in time sharing environment. This method is particularly beneficial in systems that handle multiple tasks simultaneously, such as multitasking operating system. So without wasting our time, let me continue with the objective. What is the objective of round robin? It is to evaluate the impact of different time consumed on system performance. Next, project overview. This project analyzes the performance of the round-robin scheduling algorithm by experimenting with different time quantum values. The goal is to evaluate the impact of time quantum on key performance metrics such as average turnaround time, waiting time, and the number of interrupts. This helps determine the optimal time quantum for balancing efficiency and responsiveness in process scheduling.
My name is Ranjan and I will be presenting our code. Next, we are going to have a look at the code. So for this project, we use C++ to code routing algorithm in order to read the job list and calculate turnaround time, waiting time, and number of interrupt based on the given time quantum. So the program will read the txt file, which in this case job list group 7.txt, which contain the job list and the burst time, which are already calculated beforehand. Now I'm going to run this program and we'll see. We'll see. Uh, the first thing that you see is that the program will ask you to enter time quantum that you want. So let's say I input 5 here, and then it will show the calculation for the turnaround time, waiting time, and interrupts that occur in the program. So for time quantum of 5, the average time given is 50,361.90. Meanwhile, average turnaround time is 52,218.93, and the total number of interrupt is 11,127. And lastly, the average interrupt per process is 370.99.9. Next, we're going to run this again and we use time quantum of 10 to we see the difference. Here you can see the calculation, and to the bottom the average time for time quantum of 5, the average waiting time for time quantum of 5 is 50,386.9. Meanwhile, the average turnaround time is 52,243.93. And then total number of interrupt is 5,556. And lastly, the average interrupt per process for time quantum of 10 is 185.2. And that's all from me. Thank you. Moving on.
Hello, my name is Adam and I will be presenting time quantum performance comparison. This table compares multiple time quantum values ranging from 5 to 60 units. For each time quantum, we analyze 4 primary metrics. First one is average waiting time. Second one is average turnaround time. Third one is total number of interrupts. And the last one is average interrupts per process. At a smaller time quantum values, such as 5 and 10 units, the average waiting time and turnaround time remain consistent at approximately 50,360 and 50,240 respectively. However, the total number of interrupt is significantly higher, 11,127 for a time quantum of 5 and 5556 for a time quantum of 10. This results in an average of 370.9 interrupts per process at a quantum of 5. As the quantum increases, we observe a sharp decline in the total number of interrupts. For instance, at a time quantum of 25, the number of interrupts reduces to 2215, with an average of just 73.83 interrupts per process. This trend continues as the time quantum increases to 40, where the average interrupts per process drop to 46.03. At a higher time quantum values, such as 50 and 60, the performance stabilizes further. The number of interrupts decreases to below 1000, and the average interrupts per process reaches a low of 30.3 for a time quantum of 60. Interestingly, average waiting time and turnaround time remain relatively unchanged across all time quantum values, suggesting that the metrics are less sensitive to the time quantum. That's all from me.
So hi, my name is Nurani Soda, and today I'll explain how the choice of time quantum in the round-robin scheduling algorithm impacts average waiting time, average turnaround time, and average interrupts per process as shown in the charts. So first, let's take a look at average waiting time. The data shows that smaller time quantum values like 5 result in higher waiting times around 50361.9 units and as the time quantum increases, waiting time stabilizes and slightly decreases, reaching about 50242.63 units at a time quantum of 60. So this suggests that while increasing the time quantum can help reduce waiting time, so the improvement is marginal beyond a certain point. Next, we move to average turnaround time. Here, smaller time quantum values such as 5 keep turnaround time lower at approximately 52218.93 units. However, as the time quantum increases, turnaround time grows significantly, peaking at 52899.67 units for a time quantum of 60. So this indicates that smaller time quantum values are better at ensuring faster overall completion of processes. Finally, we consider average interrupts per process. This matrix is highest for smaller time quantum values such as 370.9 interrupts at 5 due to frequent context switching. And as the time quantum increases, the number of interrupts drops sharply, reaching just 30.3 interrupts at a time quantum of 60, which is significantly improved CPU efficiency.
Assalamualaikum and hi, my name is Muhammad Hafizul. So today I will continue with the summary of the key recommendation. I will sharing our analysis of the best time quantum for scheduling tasks in the system. After testing a various value, we found that a time quantum of 30 is the most effective choice. It balances speed, fairness, and system efficiency. Let me explain why. A time quantum of 30 works best because it avoids the problem of being too small or too large. If it's too small, the system wastes time switching between tasks. If it's too large, tasks take too long to complete. Value of 30 hits the perfect balance. Here's the data to support this. First one is waiting time. It's very low at 50,336.67, so task doesn't sit idle for long. The second one is turnaround time. It's very quick at 52,240.73, one of the best observed. And the third one is interrupt process, just 78.83, minimizing wasted time and overhead. This number shows that 30 keeps the system fast and efficient. The trade-off for this is smaller time quantum costs too many task switches, increased delay. Larger time quantum lead to long task completion time. By choosing 30, we avoid both issues, achieving smooth performance. In conclusion, a time quantum of 30 delivers the best result in minimize waiting time, speed up task completion, and reduce unnecessary interruption. This ensures the system runs efficiently and effectively. I think that's all for me. Thank you.
In conclusion, round-robin scheduling is a cornerstone of modern multitasking systems, ensuring fairness, preventing any single process from monopolizing the CPU. Its simplicity and effectiveness make it a popular choice, but like any algorithm, it comes with its own set of trade-offs, such as context switching overhead. We hope this presentation has given you valuable insights into how round robin works and its role in operating systems. Thank you for your time today.